Okay, let's get started. Hello everyone. This is SeungryongKim. Hello. Before starting, I guess some of you are first time to take this class, right? Because you maybe change your class. Welcome. And if you are first time, please check our introduction lecture. You can access the first lecture in our YouTube website. Please check that. And yeah. Okay, so because there are some new stuff, okay, I'd like to take some questions. So do you have any question for this class? No? Okay, so that's it. And our, okay, so actually this is lecture 2.2, right? So if you want to see our previous lecture, I mean the Tuesday lectures, please visit our YouTube channel as well. You can freely see that. What's that? Okay. So yeah. 여러분 오늘 일단 반갑습니다. 처음 오신 친구들이 좀 있는 것 같은데 화요일날 오픈 친구들이 좀 있네요. 우리 이제 좀 해야 되는 것들이 있어요. 우리 이름을 좀 바꾸기도 해야 되고 벌써 다른 친구들 잘 바꿨죠? 일단 인트로를 한번 보고 오셨으면 좋겠습니다. 그래서 저번 시간에 했던 거 저희가 리코디드 파일에 블랙보드 올라가면 볼 수 있으니까 보고 저번 화요일 수업도 여러분들 좀 보고 뭐 오늘은 일단 넘어가고요. 다음 시간까지 좀 보고 오면 좋을 것 같아. 됐죠? 처음 오는 친구들 혹시 뭐 질문 있으면 편하게 해주시고. 오케이, 반갑습니다. 아마 이제 수완 변경이 끝난 걸로 알고 있고 이제 여러분들은 좋든 싫든 이제 저랑 한 학기 동안 가야 되는 친구들이네요. 그렇죠? 잘해봅시다. 자, 우리 오늘 오케이. 자, let's get started. So today we will start with elementary operation. Okay, before starting, I'd like to recap. So we started with the definition of the linear equation, definition of the solution and solution set, and how to solve this linear system. In your high school and middle school, you just find the solution with intersection of the two lines or the plane. And there are three kinds of possibility of the solution set. Exactly one solution, no solution, infinite solution. Consistent, right? A system is consistent if there is at least one solution. Otherwise, it is inconsistent, right? And equivalent, right? In this case, linear system 2 is equivalent system of the linear system 1, or linear system 1 and linear system 2 are equivalent each other. We also introduced the matrix, right? So when you just consider the coefficient, we can say that this is the coefficient matrix. If we consider the right-hand side on the linear system as well, it's going to be the augmented matrix, right? The size of matrix is defined like that: m rows and n columns, or m by n, or n times n, right? And the definition of the row, please remember this page. 그렇죠? 이렇게 row가 이렇게 컬럼 이렇게 생겼다는 거. And we discussed the vector, matrix, and tensor. So tensor is the core representation in many applications or discipline. The deep learning or the convolutional neural network is one of them. So the building architecture of the convolutional neural network consisting of the tensor representation. That's why we learn this kind of linear algebra. To find the solution, then our strategy is to replace one system with the equivalent system that is easier to solve. Right? So we see very simple example: solving given system equation with the 가감법 in Korean. So yeah. So what was our strategy? Just remaining one variable per each row, each columns here, right? So we do this with some kinds of equation, multiplication and equation, arithmetic, mathematics between the equations. Then we finally achieve this very simple linear system comparing to the original linear system. But these two linear systems are equivalent. So we can say that the solution set of this linear system is exactly the same as the solution set of the original linear system, right? That's it. So yeah, this right. So as we discussed Tuesday, now we have a matrix form, right? So we need feel the more system way to work in a matrix form, matrix space, which is going to be the much easier to understand and much easier to solve in case that if you have very large scale linear system, for example, the billions of the variable or the so many number of the matrix equations, right? So to this one, I'd like to introduce three kinds of the matrix operator. Replacement, interchange, and scaling. Replacement, interchange, and scaling. 실시간 대화 사용이 뭐지? 네, 실시간 대화 사용 됩니다. 네, okay. So replacement is very simple. Okay, let's suppose that this is the first equation and this is second equation. We want to replace one row by sum of itself and multiple of another row. Sum of itself or multiple of another row. For example, okay, let's say this is R1 and R2. And if we want to R1, new R1 is equal to previous R1 plus 2R2. If we want to do this kind of operator, yeah, in this case, our new R1 is going to be the 6 plus 2 by 2 and 3 plus 2 by 1 and 1 plus 0 times 2, right? And the second equation is 2, 0, 1, right? And our new matrix is going to be the 10, 2, 5, 1, 1, 0, right? So this is the replacement operator. This replacement operation or operator, right? And another very frequently used operator is interchange. 이거 왜 자막이 나오죠, 저희? 민망한데요? 이거 아까 수락해서 그렇구나. 네. 있는 게 편한가요, 여러분? 자막 있는 게 편해요? 어떻습니까? It is fine for you to use the subscript. No? Yes? This is up to student. Okay. 아, 그래요? How can I turn off? 어떻게 그죠, 이거? 민망한데요, 약간? 잠깐만요. 이거 어떻게 그죠? 이럴 수 있는 메뉴. 네, 합시다. Okay. Let's continue. So another operation is the interchange. We want to interchange two rows, R1, R2, for example, and we want to interchange R1 and R2 like this, and our new matrix is going to be 1, 4, 9, 0, 2, 3. This is examples of the interchange and scaling. Just multiply whole entries in the row by non-zero constant. For example, I'd like to achieve new R1 1/5 times R1 like this. Then our new matrix is going to be 1, 1, 1, 0, 0, 0. This is the replacement operator, interchange operator, and scaling operator. In other words, if there is a sequence of the elementary operation between two augmented matrices of the two linear system, two matrices are called row equivalent. Row equivalent. For example, okay, so let's suppose that we have original matrix like this, original matrix like that. First of all, if we want to multiply by 2 on R1, we can achieve this matrix like this, right? If we apply scaling on row 1 again by 1/2, we can achieve another matrix looks like this: 2, 1, 5, 2, 3, 8, right? Or if we apply, for example, interchange R1 and R2, then our new matrix is going to be 2, 3, 8, 4, 2, 10, like this. So as you can see here, these 4 kinds of matrix are row equivalent because they each linear system can be generated by sequence of elementary row operation, as you can see here, right? So in this case, we can say that this is row equivalent, right? Okay, if augmented matrix of two linear systems are row equivalent, then the two systems have the same solution set, right? This is our strategy, right? Let's also assume that this is original, our linear system. If this one is much easier to solve than original augmented matrix, we can easily find our solution set, which is going to be the solution set of the original linear system, right? So this is our strategy. I mean, how to derive this easier to solve, for example, easier to solve linear system by using a sequence of elementary row operation. This is today's topic. Okay. Okay. Before that, I'd like to introduce 2 more concepts: existence and uniqueness. We already talked about this one in the possible solution set. There are 2 fundamental questions about the linear system. Okay, let's suppose that you have a linear system, your own linear system. There exists 2 questions. Is your system consistent? And if the solution is unique? First question is relevant to the existence of the solution. And second question is the uniqueness of your solution. Uniqueness of solution. So whole of your linear system can be described by 2 questions: consistency, uniqueness, or existence and uniqueness, right? So I'd like to show you the one example. So the example 2, determine if the following system consistent. So the consistent mean, what's the meaning of the consistent? 뭐였죠? consistent meaning. 자, consistent하다. 그렇죠? At least one solution. 그렇죠? At least one solution, right? Exactly one solution or infinite many solution. Anyway, there should be a solution, right? Okay, so this is our original linear system, right? In fact, we already saw this linear system in our previous example. 그렇죠? example 1에서 벌써 풀었죠? So we already know this one can be reduced this kind of linear system, right? This kind of linear system. Then, of course, corresponding augmented matrix of this form, it looks like this, right? So, as you can see here, as you already talked about this one, this linear system had solution, and a solution exists, right? So we can say that the system is consistent, right? What's the solution of this one? What's the solution of this one? 뭐 very straightforward였죠? 어떻게 그랬죠? 뭐 x3 was 3, right? And by substituting x3 on here, we can achieve x2 minus 12, 4. So x2 is going to be 16 in this case, and x1 should be 2x2 minus x3, and 2x2 is going to be 32 minus 3, so it's going to be negative 29. So x1 is 29, x2 is 16, and x3 was 3, right? So solution is consistent, right? Or the system is consistent. The second question is, solution is unique or not? In this case, unique or not? 자, unique 할 때가 안 할 거 이럴 때. 저 unique, right? 저 here was that. Unique. So we can say that this system is consistent and unique, right? Or their solution is exist and solution is unique, right? So this is the way to describe your own system. Let me move to the another matrix, another linear system. Determine if the following system is consistent, right? So we have a system like this. So to answer this question, we have to solve this linear system, right? We already discussed how to solve linear system in example 1, but from now on, let's work on matrix domain, okay? Augmented matrix domain with elementary row operation, okay? So we already have 3 kinds of elementary row operation, right? What's that? Replacement, and interchange and scaling, right? So by using one of them or both of them or all of them, let's find out new augmented matrix which is equivalent to the original linear system, but which is much easier to solve, right? So let's do that. Okay. So if we represent this linear system in an augmented matrix, it should be looks like this. Because there is a 0, our augmented matrix is going to be 0, 2, 5, blah, 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 right? So our strategy is similar. We want to limit one single term at each column, right? And each column. When you see the column 1, there is 2 values, right? So we want to eliminate one of them, right? But before that, we would like to make this one as a 1, this one as a value 1, because this kind of strategy has the many benefits. I will let you know soon. Anyway, I would like to make this term as a 1. So first of all, how can I do that? Okay, if we say that there's R1 and R2 and R3, by just replace R1 and R2 or R1 and R3, we can achieve this term is not theorem, right? Okay, let's do that first. So to obtain x1 in the first equation, interchange row 1 and row 2 first. Interchange row 1 and row 2, but you can interchange row 1 and row 3. Anyway, in this case, let's interchange row 1 and row 2. That's right. So row 1 and row 2 interchange. Right? Then we achieve new augmented matrix, which is equivalent to the original matrix. Right? Right. Then what do you want to do next? We would like to eliminate this term, right? How can you do that? By using the first equation, right? So to eliminate 5x1 in the third equation, add -5/2 times row 1 to the row 3. So it's going to be the replacement operation. R3 minus original R3 -5/2 R1. Like this. So this is R1, right? This is R1. And -5/2 times R1. It's going to be 얼마 되죠? -5 50/2. Please let me know if I wrong. 5 -5 or -5/2, right? And original row 3 was 5 -8 7 1. Okay, by adding these two equation, we achieve 0 얼마요? -1/2 and 2 and -3/2, right? So this is a new matrix, this new row 3, right? So by using this kind of row operator, replacement 써볼까요? Interchange and row operation. 미안해요. row operation이 맞는데 replacement. We achieve new augmented matrix. 승부? Question was that I can't read what you wrote below the interchange. 여기 미안해요. 그 scaling. 요거 scaling. Replacement, interchange, scaling. Thank you very much. And what next? Okay, we make a unique term in column 1. Then let's do similar things in column 2, right? How can we do that? Our strategy is similar to the example 1. By using this one, just remove this term first, and then make this term removed again by using the next equation, right? So in other words, our strategy is that we want to make our new equation in a form it looks like this: upper triangle, the inverse triangle like this, right? So first of all, let's remove this term first. 그렇죠? Let's suppose that this is R2 and this is R3. How can I remove this term? 자, 어떻게 지우죠? How can I remove this term in R3? Maybe R3 plus 1/2 R2 하면 지워지겠죠? Replacement, right? use x2 in the second equation to eliminate negative 1 over 2x2 from the third equation. 그래서 just add 1 over 2 times rho 2 to the R3. 그래서 뭐예요? 다시 쓰면 뭐겠죠? 뭐죠? rho 3가 new rho 3 is going to be R3 plus 1 over 2 times R2. Because this is first time I load each detail, but after that I will just skip because you can easily follow this one, right? I strongly suggest you solve yourself. Okay. Anyway, original R3 was then negative 1 over 2 to negative 3 over 2. Negative 1 over 2. So, 2, negative 3 over 2, and 1 over 2 R3. It's going to be 1 over 2, negative 2, 그쵸? 4, right? Then by adding these two terms, it's going to be 0, 0, 0, 0, and 뭐예요? 8 over 2, so it's going to be 5 over 2. So this is the new rho 3, right? Okay, so we achieve this new augmented matrix. So by this one, we make augmented matrix in a triangular form, like this. Right? So to interpret it correctly, this is augmented matrix. So let's go back to the equation form like this. So 2x1, negative 3, x2, 2x2, 1, 1, 1x1, 1x2, negative 4x3, 8, 0, 5 over 2, right? Okay. So what is the solution of this form? What is the solution of this equation? I mean linear system. 자, 이 경우 solution 뭐죠? In this case, what is the solution of this one? Right? Inconsistent, right? Why? Because of here. So there is no equation 0 equal to 5 over 2, right? It's impossible, right? So in other words, we can say that there's no solution, and this system is inconsistent. Right? Okay. There are no values of x1, x2, and x3 that satisfy this because the equation 0 is equal to 5 or 2 is never true. And we already know because we just applied the law operation, elementary law operation, for example. We just applied the law operation, this original system and this original system are equivalent, law equivalent, right? In other words, original system is inconsistent. That is, it has no solution. Right? This system is inconsistent because there is no point that lies in all three planes. So if you remember the way to represent three-dimensional space, I mean the three variable equation, let's suppose x1 and x2 and x3, original matrix consisting of the three equation fill three planes like this, right? When we draw these kinds of the three planes, there is no intersection. So in this case, no solution, and inconsistent. Right? That's it. So, okay, let's compare example 1 and example 2. So the solving strategy was similar, but by just using the augmented matrix and row operation, we easily derive new linear system that is easier to solve. Looks like this and looks like this. Finally here, right? So, in other words, if we go back to the equation 1, example 1, rather than working on the equation form, now we can work on a augmented matrix form here, 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 by using the row operation. So it's going to be the homework. So please derive example 1 again in a matrix operation with a matrix operation. Okay. 근데 이제 여러분들 뭐 봐서 알겠지만 매트릭스 오퍼레이션이 훨씬 쉬워요. 쉬운 것뿐만 아니라 이제 우리가 앞으로 배울 것 중에 많은 프로퍼티를 쓸 수가 있어요. 그래서 이제 우리가 이런 것들 이제 오퍼레이션, 매트릭스 오퍼레이션 풀 수 있다라는 걸 이제 보여주는 거고, 여러분들이 한번 홈워크로 한번 이걸 해봐요. You necessarily submit this homework, like this homework. It's going to be the your own homework. So please try to solve yourself. Okay. Question. Hongmin 학생, Professor, could you please explain replacement operation? It's quite difficult. I mean, how can I letter equation be the original equation? How can I letter equation be the original equation? Do you mean how to make this matrix to this matrix, okay? Right? Yes. Oh, it's quite straightforward, right? How can you do that? 자, 누가 한번 대답해 볼까요? How can you do that? 이거 어떻게 하면 돼요? 보면 어떻게 하면 되죠? R1을 다시 한번 반대로 해두면 되죠. R1 마이너스 2R2 하면은 나오죠. 그렇죠? 인버스 오퍼레이션. 그렇죠? Right? 그렇죠? Okay. You mean? I mean, why that operation work? Sorry, 뭘 모르겠다는지 모르겠네. Why the operation works? 그러니까 왜 이 두 개 이퀴벌런트하지 모르겠다는 거죠? 그렇죠? 아니면은 in fact, by definition. So next chapter we'll talk about why this definition works. So let's just wait. Okay. 다음 챕터 가면 이제 그 얘기가 좀 나와요. 알겠죠? 그러네. 나중에 행렬고 배우시면 알게 될 거예요라고 벌써 알려줬네요. 네. 자, 너무너무 좋은 질문이고 너무너무 당연히 나와야 되는 질문이에요. 알겠죠? Okay, so that's it. So it was the chapter 1.1. Now let's move to the chapter 1.2. Row reduction and echelon form. We already talked about row reduction and echelon form, but in this chapter we will systematically define row operation and row reduction and echelon form. Okay. Okay. Yeah. So here we have to define two more concepts. Non-zero row or non-zero column in a matrix means a row or columns that contain at least one non-zero entry. So for example, this one is zero row, but this one is non-zero row. Why? Because there is a non-zero term, right? This. or non-zero entry or non-zero term, or this one, this column, first column 4, 0, 0, it's not a zero column. It's going to be non-zero column because of 4, right? This is definition of the non-zero row or non-zero column. And one more thing is that leading entry. Leading entry of the row refers to the leftmost non-zero entry in a non-zero row. Leftmost non-zero entry in a non-zero row. So, for example, this one, leftmost non-zero entry here. This one is the leading entry of row 1 or first row, right? And this one is leading entry of row 2 or second row, right? So this is the definition of the leading entry. Okay. So by using this concept, let me introduce echelon form. Echelon form, or just called EA. So echelon form should satisfy these three statements, these following three statements, 1 to 3, right? First of all, whole non-zero rows are above any rows of whole zeros. In other words, whole zero rows at the bottom. So for example, this is a zero rows, right? And whole non-zero rows are above any rows of the all zeros, right? So this is a first statement, right? The second statement means each leading entry of the rows, in this case, 어디였죠? leading entry가 here and here, right? Is in a columns to the right of the leading entry of the row above it. Leading entry of the row is in the columns to the right of the leading entry of the row above it. 무슨 뜻이야? 이런 거죠. This is the leading entry of second row. This is the leading entry of the first row, and this leading entry is right side. 그쵸? 오른쪽, right side of leading entry above it, right? 그래서 이 3이 4보다 오른쪽에 있는 형태가 된다는 거죠. 그렇죠? Just definition, right? Finally, whole entry in the columns below the leading entry are zeros. So in this case, whole entry in the columns below or leading entry here should be 0. 0, 0, 0, 0, because this is leading entry, right? If a matrix satisfies these three kinds of statement, we call this one is the echelon form. Okay, so let me show you something. Okay, let me give you an example. What if we have matrix 1, 1, 6, 1, 2, 3, 0, 0, 0. This one is echelon form or not? Question. echelon form or not? No. Why? 왜 아니죠? Why? 아우, 여러분 반응이 너무 좋네. 왜 아니에요? Because the one in the second row, right? So each leading entry, in this case, leading entries are here and here, right? So it does not satisfy the second statement, right? So in general, if a matrix satisfies this echelon form condition, the matrix looks like this. in general looks like this. So there are leading entries are here or here, and this term should be zero, and this term can be any kind of value, right? This is the general form of the general form of echelon. Why we need echelon form? By the way, echelon form in Korean, 이게 한국말로 하면은 사다리꼴, 그죠? 바로 느낌 딱 오죠? 사다리꼴 들으니까. 자, 이렇게 생긴 거. Why we need this one? Why we need this one? As we discussed in previous examples, if we apply this kind of matrix, we can easily solve the solution, right? Compared to the original matrix, right? So to conclude, we would like to derive echelon form of the matrix. I mean the echelon form of original augmented matrix. This is going to be our new strategy, right? Anyway, this is echelon form. 그렇죠? 그리고 echelon form 왜 배우냐? 자, 조금 더 시스테믹하게 정리하자고 했죠? 우리는 오리지널 매트릭스를 어그멘티드 매트릭으로 바꿨을 때 그 어그멘티드 매트릭스를 에슬런 폼으로 바꾸는 걸 하고 싶다라는 거예요. 오케이? 그 에슬런 폼이 뭐냐? 요거를 만족해야 된다. 오케이? 너무너무 쉽죠? One more thing is that reduced echelon form. Narrow echelon form, reduced echelon form were called REF. REF. REF should satisfy these three statements as well as two more statements. First one is that leading entry in each non-zero row is 1. So here's the example. Leading entries are here and here and here, and each non-zero row, I mean the leading entry is 1, right? 1, 1, 1. Okay. And second thing is that each leading one here is the only non-zero entry in each column. So as you can see here, in column 1, this leading entry is the only term that have values. In second column here, right? In third column here, right? And remaining part 0 values, right? So this kind of form is called reduced echelon form. Reduced echelon form, right? Or in general, we can represent this reduced echelon form in this kind of term. So this kind of form, so reduced echelon form. Right. So let's go back to our system. For example, we would like to solve original linear system, right? But if we have this kind of reduced echelon form, let's also assume that this is augmented matrix, then we can easily solve the solution set as x1 is 1, x2 is -3, -6, x3 is 12, right? So in other words, if we can make or if we can find reduced echelon form of the original augmented matrix, we can just solve the system, right? This is going to be our new strategy. In other words, okay, let's suppose that we have a augmented matrix, original augmented matrix, consisting of n rows and m columns. M column, right? We already talked about row operation, right? Row operation, so replacement, interchange, scaling, right? By using row operation, if we can make a new augmented matrix that shape like this, I mean the echelon form, we can determine there exists solution or not. There exists solution or not. 그렇죠? And if we going further, if we going further with the more row operation, then if we can achieve new augmented matrix in a REF form, it should be looks like 1, 1, 1, blah, blah, 1, 0, 0, and sub values, right? Then we can directly solve the solution of this one in REF form, right? In other words, the solution of this REF form is going to be the solution of the original system, right? That's what I want to do in this section, right? So, in other words, our new strategy is going to look like this. If we have the original matrix, first we want to make an echelon form of the original matrix and further row reduce the reduced echelon form, okay? And find the solution, which is going to be the solution of the original system, right? Which is exactly the same procedure that we discussed in example 3, 3, right? So this is original augmented matrix, right? And we make a echelon form matrix, right? To check there is solution or not, right? And then if there was solution, by making this term as a REF form, we find the solution. So we can see this one in example 1 here. So it was the EF form, echelon form, and by going further, we achieved this one. In fact, it was REF form. 그렇죠? 조금씩 감이 오죠? 그래서 우리가 이걸 풀었던 게 결국에는 EF 폼과 REF 폼, 에슬론 폼과 리듀스 에슬론 폼을 얻어오는 과정이었다라는 거죠. Okay? So that's the definition of the EF echelon form and reduced echelon form. Okay. Okay. There are some properties on echelon form. Echelon form or reduced echelon form is one that is in echelon from echelon form or reduced echelon form. So, in other words, if a matrix in an echelon form, we just call this is the echelon matrix or reduced echelon matrix. 그렇죠? Echelon matrix or reduced echelon matrix. One more property is that any non-zero matrix may be a row reduced, transformed by elementary row operation. 그렇죠? What's that? replacement, 뭐예요? interchange, scaling, 다 들리죠? replacement, interchange, scaling into more than one matrix in an echelon form. One matrix, echelon form, right? In other words, okay, let's suppose that we have a matrix, our original matrix, let's say M. By using sequence of the row operation, we can row reduce original matrix to the echelon form. But it's not unique. There, it's going to be more than one matrix. So in other words, there are many kinds of the echelon form possible, like this, by using different sequence of the elementary operation. However, the reduced echelon form obtained from the matrix. 오타가 있네 여기. obtained예요. Reduced echelon form, one obtained from the matrix, is unique. So, if we going further, this whole echelon form can convert it to the 1 REF form. Why? Because this whole procedure done by row reduced, or row reduction. So solution set of whole augmented matrix should be exactly the same. So solution set of this one, and this one should be the same, right? That's this kind of properties occur, right? So this is properties of the echelon form. So here's the theorem. This is the first theorem this semester, right? 자, 여러분들 너무너무 자, 우리 이번 학기 처음 theorem이 나왔어요. 우리가 아마 이번 학기 끝날 때쯤에 한 10 몇 개 정도의 theorem을 볼 건데, 자, 이것부터 봅시다. The theorem mean? What's the meaning of the theorem? 자, 우리 언제 theorem이라고 하죠? 자, theorem이 무슨 의미예요? What is the meaning of the theorem? Why we have to know the theorem? 자, 우리 theorem을 왜 배워야 되죠? 우리 막 생각해 봅시다. 우리 중학교, 고등학교 때 수학 배울 때 이게 뭐라고 그러죠? 한국말로 치면은 정의죠, 정의. 이론, 정의라고 표현하죠. 이걸 왜 배웠지? 우리 한국말로 배우면 이제 우리가 아마 이번 학기에 많은 theorem들을 배울 거예요. 갑자기 질문들이 없어졌는데, 자, 이거 한번 답해볼 친구 자신 있게. 자, theorem을 왜 배우지 우리가? theorem들을 use easier. Yes. Others? To do something faster. Yes, right? 다른 문제 해결할 때 이용할 사용할 수 있기 때문입니다. To solve the question easier. 다음 소그래프. 아이고 너무너무 다들 똑똑하네. 맞아요. 다 맞는 말이에요. The thing is, this is just the definition and appointment among the people, right? So if we define theorem is like that, and this theorem is proved by something, we can just use this theorem after that because the true or false statement were already proved. 그렇죠? 그래서 이제 우리가 theorem 쓰는 이유는 뭐냐? 약속, 결국 약속이에요, 사람들끼리. 이 약속을 뭐냐? 증명이 된 약속. 뭐냐? 그럼 그 약속은 이제 증명이 됐기 때문에 우리가 쓰면 돼요. 그냥. 그렇죠? 그래서 우리가 뭐예요? 예전에 우리가 막 그런 얘기 배우죠. 대학교 다닐 때, 고등학교 다닐 때 수학은 암기 과목이 아니다. 뭐 이런 얘기 배우죠? 그렇죠? 말했었죠? 수학은 암기 과목이에요. To some extent, right? We have to memorize some theorem, right? To accelerate your solving procedure, right? Because previous people already proved this concept, so you don't need to derive this one from scratch. You can just use this one, right? Anyway, that's why we have to know this theorem. So this is the first theorem, uniqueness of reduced echelon form. Okay. In previous slide, I just said that reduced echelon form, one from the matrix was unique. And here was the theorem, uniqueness of the echelon form. Each matrix is row equivalent to the one and only one reduced echelon form. So each matrix and every matrix should be reduced to single or unique reduced echelon form. Okay. Unfortunately, this proof requires concept not introduced yet, so we can't prove yet. So here, just remember, just memorize. 사실 첫 번째 theorem에도 불구하고 우리는 이걸 증명을 못해요. 아직 우리가 배우지 않은 컨셉들로 증명을 해야 되기 때문에 일단 첫 번째는 우리가 이해를 하고, but I just want to some examples of the why reduced echelon form is unique. Here's things. Here's the one matrix, another matrix, and another matrix. If we apply scaling operation here, R1, 아니죠. Interchange operation R1 and R2. Then we achieve this one, right? And if we apply R1 minus R1 is equal to R1 minus 2R2, then we're gonna achieve 0, 1, 0, 1, 0, 1, 0, right? So it is called REF form, and this is called EF form, right? But as we discussed previously, there will be another echelon form. For example, why not using different elementary operation? For example, I want to transform original matrix to the 1 over 2, 2, 1, 2, 5 by R1 by scaling, right? R1 is equal to 1 over 2 R1. Right? Then by just adding this one, I mean the just substitute the subtract, because subtract is also added, right? Minus 1 added, right? And our new matrix is going to be 1 over 2, 2, 0, 3 over 2, 얼마죠? 1 over 2니까 빼면은 3, 그렇죠? Right? 어떻게 나오죠 이게? by R2 minus R1 하면 되죠. Replacement, right? And then by dividing this matrix, I mean the R2 as a 3 over 2, this is going to be 1 over 2, 2, 0, 1, 2, 그렇죠? Then by subtract first equation minus second equation by 1 over 2, it's going to be 1, 0, 1, 0, 1, 2, right? So here it was another echelon form of the original matrix. Another echelon form matrix, but this one row reduced the same REF form from here or here. Okay, this is just the proof of the theorem 1. Okay. Anyway, let's just simply use this theorem 1 to solve further question. One more definition is if matrix A is row equivalent to the echelon form matrix U, we call matrix U is echelon form of matrix A. 그렇죠? So A is row reduced to the U, which is echelon form, and U is in the REF form, is in reduced echelon form. We call U is a reduced echelon form. Reduced echelon form. So this is definition of the echelon form and reduced echelon form. And one more concept is pivot position. Pivot position. We discussed this kind of the definition to derive the row reduction algorithm, which is the core of this chapter. But it's going to be the systemic definition of our previous problem solving. So you don't need to worry about so many definitions. It's just definition. Okay. So one more thing is that pivot position. 자, 우리 오늘 리딩 앤 트리드 배웠고 이제 pivot position 나왔어요, 그렇죠? 정말 간단해요. Pivot position in matrix A is the location that corresponded to the leading one in reduced echelon form of matrix A. Reduced echelon form of matrix A. So this is the REF form, right? So this is REF form, right? Because there are leading entry 1 here, leading 1 or leading entry 1, and there are remaining part are 0, right? So this is REF form. REF form. So pivot position means the position or location that corresponds to the leading one. So here, here, here. So these are called the pivot positions. Right? Pivot position. And pivot column means a columns of A that contain a pivot position. So in this case, this column 1, column 2, column 3 are pivot columns. Pivot columns because they contain pivot position. Okay. Question so far. Question 어렵지 않죠? Okay. To understand this one in detail, I'd like to show you one more example. So the question was load this matrix A below to the echelon form, 그쵸? EF form이었죠? And locate the pivot columns of A. Locate pivot columns of A. Okay. So to locate the pivot columns of A, we have to know position of the leading entry, right? So which is going to be the pivot position, right? It's very easy. So to do this then, we have to row reduce matrix A. row reduce 뭘로 해야 되죠? by elementary row operation. Okay. So let's do that. So in this case, we have a 4 rows and 5 columns. And if we assume this is the augmented matrix, we have the 4 variable. Okay, let me see. Now let's write that. So we have a 4 rows. So we have a 4 equations and 5 columns. And if we just assume this is augmented matrix, we just have the 4 variables, right? Okay, let's row reduce this original matrix to the echelon form. Okay. 자, question so far. 우리 오늘 여기까지는 할 건데, question. 쉽죠? 한번 해봅시다. So first of all, the top of the leftmost non-zero column is the first pivot position. 그렇죠? Non-zero entry or pivot must be placed in this position. It's very important to note. Leftmost non-zero column is the first pivot position. Why? By definition of the echelon form, right? If here 어떻게 써볼까? 여기서부터 써볼까요? 여기서 이렇게 써봅시다. Like this. 이거를 이렇게 써봅시다. If our matrix simply represented by 0, 1, 0, blah blah 0, 1, 1, 0, 0, 0, 0, 1, blah blah things, right? In this case, it's not a REF form, right? Right? So to be the REF form, we have to replace these two terms. Then it's going to be the 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, blah blah blah. So in other words, the first entry, the first pivot position always must be placed in this position. Okay. So this is our starting point. So how can I do that? Because this is our original matrix, so but there was a 0 in the first element of first row, then we can just replace R1 and R4. But there might be other possibility, but it's going to be a much easier solution, right? Because we already have the 0. We already have the 1 here, right? So just interchange R1 and R4, then we're going to have this one matrix, right? So right. So what are we going to do next? We want to make this term and this term as 0, 0, 0, right? To make reduced echelon form, right? Or echelon form. So by using this R1, we can load it, we can manipulate R2 or R3. How can I do that? Okay, let's suppose that this is R1, R2, and R3. Our new R2 should be R2 plus R1. So to remove this term, and our new R3 should be R3. 그렇죠? 여기 R3 should be R3 plus 2R1. 그렇죠? Plus 2R1. So let's do that. There was nothing special on R1. 1, 4, 5, -9, -7, and second new row 1, new row 2 is going to be the -1, -1, -2 plus 4, -1 plus 5, 3 minus 9, 알겠죠? 9, 그렇죠? 1 minus 7, 그렇죠? The third one is going to be 2 plus 2, -3 plus 8, 0 plus 10, 3 minus 18, -1 minus -14. And remaining term, I mean the first row, just 0, -3, -6, 4, 4, right? Then it's going to be, 아니죠, should be +1, right? So it's going to be 0 and 0, and we can calculate this one, right? Remaining one. By doing this, okay, create 0 below the pivot 1 by adding multiples of the first row to the 2 rows below, obtain the next matrix. Then our new matrix is going to look like this. Okay. Okay. So first of all, in this case, this is the pivot position. And this is pivot column. Columns, right? Pivot column, just pivot column. Okay, right? Question? Any question? And we already made this one in a partially earlier form. Then we can do similar thing on here, right? Here. How can I do that? Because our goal is to make, here, echelon form. Let's forget here and let's just focus on here to make this matrix as this kind of form. 그렇죠? 그래서 the next thing we want to do is just remove this term and this term by using this value. In other words, by using the R2 just to manipulate R3 and R4, right? How? New R3, maybe it's going to be R3 minus 5 over 2, R2, and new R4, it's going to be R4 plus 3 over 2, R2, right? Then, 여러분 열심히 계산해 보세요. Then, our new matrix is going to be looks like this. Right. Right. And we already know this is a pivot position. And in an echelon form, we easily expect this one will be the leading one in relief form, right? So by just divide 2 here, so we can say that this is the pivot position, and this column is pivot column. Pivot column, okay, pivot column, right? And let's go in deeper. And okay, we already have 2 pivot column and remaining part here, because we don't need to consider this part, right? We only interested in the here to make echelon form, right? Let's work this one, but there are whole zero in this case. There are whole zero in this case. So what should we next? Let's just interchange to make this term as a new leading entry, right? So from here, just to interchange R3 and R4, then we are going to have this kind of the relief form, right? This is a no, not relief form, just echelon form. Echelon form, okay, or EF form. In the EF form, we produce leading entry in here, right? So this is going to be our new pivot position. Okay. So in other words, okay, there was 3 pivot position here, here, and here, right? So if we go back to our original matrix, but pivot position does not change. So in final, I mean the original matrix, this location, and this location is called pivot position. Pivot positions, and row 1, column 1, column 2, and column 3 are called pivot columns. But columns. Okay. Okay, so this is the definition of the pivot position and pivot columns. Okay. Question so far. Hyungmin 학생 professor, is that matrix coefficient method and is a certification non-zero row? Verify other comment. I wrote this comment when I learned EF for the first time. In this example, I just assumed that this is the augmented matrix. Sorry about that. This is augmented matrix, not a coefficient matrix. Yeah. Anyway, in this case, you don't need to worry about. You don't need to consider, because this is just the definition. In this example, we want to just learn the definition of the pivot position and pivot columns. Okay. Any other question? No. In fact, nowadays we have so many definitions. Then by using whole of this one, next week we will derive row reduction algorithm, which is going to be the very, very powerful way to solve linear system or system of linear equation, right? So it's going to be the final goal of this chapter 1. I mean the from 1,1 to the 1,2. Okay. 그래서 이제 우리가 오늘 뭐 많은 데피션들을 막 배워왔죠. 근데 결국에 뭘 하고 싶은 거냐면 그 데피니션들을 뭐 어디다 쓸 거냐면 요 로 리서치 알고리즘을 정의를 내릴 때 그 많은 데피니션들 컬럼이 뭐냐 리니어리티가 뭐냐를 배워서 요거를 하려고 하는 거예요. 지금 에슐런 폼과 리듀스 에슐런 폼이 들어가는 요 알고리즘을 우리가 정의를 내리려고 열심히 배우고 있는 거고, 다음 시간에 이제 요 알고리즘까지 완벽하게 배우고 이걸 통해서 얼마나 우리가 쉽게 이제 리니어 이퀘이션을 풀 수 있는지 한번 얘기를 해보도록 합시다. 알겠죠? Okay, so any other questions so far? No? Okay, that's it. So this is the end of today's lecture. Thank you very much. And we will see next Tuesday, right? And by the way, 수강 신청이 끝났죠, 여러분? 여러분 혹시 수강 신청 변경 끝났나요? 아, 끝났구나. 좋습니다. 이제 여러분들은 저랑 좋든 싫든 이제 같이 가야 되니까 한번 열심히 한번 가보도록 합시다. 오케이? 오케이. No more question, right? Okay, thank you very much. And this is the end of today's lecture. Thank you very much and see you next week. 여러분들 오늘도 수고하셨습니다.